So next we want to talk about confidence intervals and what is a confidence interval and how to interpret it. So in order to do that, we have to sort of talk about the central limit theorem, which we've already sort of alluded to with the sampling distribution. So what it says is that as your sample size increases or approaches infinity, the distribution of that mean of your sample approaches a normal distribution. So that's all the central limit theorem says, and we've already sort of talked about that a little bit. And that sampling distribution is going to be normally distributed with a mean of the population mean and a variance of the population variance over the size of the sample. And that's useful because what we want to do is, like we said before, if we want to approximate either the mean or the variance of the population, we can do that based on our sampling, the sample that we've taken. And like previously we said, we can convert a sampling distribution, a normal distribution to standard normal, and we use this equation here. And what's really, really interesting about the central limit theorem is that this is true, so the sampling distribution becomes normal regardless of the distribution of the population. So you can have a heavily, heavily skewed population that's not normal, but your sampling distribution from that will be normal. The more skewed a population distribution is, the higher the sample size that you're going to need to make this true. Okay, so how does this help us? Again, so this comes back to interval estimation or confidence interval calculation. So if we say that, again, so we don't know the mean of a population, but we want to estimate it. What we do is we take a random sample from that population, and we so again, we don't know the mean, but we know the variance. We can estimate the mean of that population within 95% confidence or 95% probability using sort of the normal distribution, the standard normal distribution, as we said before, using this equation here. So you take the mean of the sampling distribution, you find that Z value for whatever in our case it's 95%, and it's two-tailed, so you take the 0.05 and divide it by 2. This is just a standard, it's 1.96 for two-tailed 5% test, and multiply it by the standard deviation of the sampling distribution. So essentially that's what you're calculating. And what is a confidence interval? So this is important. So the confidence interval essentially tells you that in repeated samples from the population, the true value of the population parameter, in this case the mean, will be contained within 95%. It will be contained within that 95% confidence interval. So it's not that the mean value is always a constant, and your confidence interval shifts around that. It's not the other way around. And obviously, you can do confidence intervals for anything. So with respect to confidence intervals, so we talked about if you do know the population's variance, you can calculate a Z statistic. If you don't know the population variance, you have to use your sampling distribution standard deviation or variance. And it's still a normal distribution, but it's not a standard normal. It's actually a t distribution with n-1 degrees of freedom. So it's a slightly different calculation, but this is what you're actually using for like your t-test and your ANOVA is a t distribution. So slightly different. Okay, so let's move on to type 1 and type 2 error. So in order to talk about type 1 and type 2 error, you sort of have to talk about hypothesis testing when you're doing studies or reading studies. So there's always two hypotheses. One is the null hypothesis. And the null hypothesis essentially says that there is no difference between whatever you're looking at. And the alternative hypothesis, which just says there is a difference. And that difference can be a difference in general or a greater difference or a less than difference, which is one-sided versus two-sided test, and we'll look at how that differs. Whenever you're doing any study, the challenge is you can never prove the truth of something. All you can do is you always test the null hypothesis, and you can either reject the null hypothesis or fail to reject the null hypothesis, and that's all that this says. You can't say that either one is true. So these are the hypotheses, and these are just how you denote them. So for this is the null hypothesis for a one-sided test, whereby let's start with two-sided. So the two-sided test says that the null hypothesis is that there's no difference between two values, and the alternative hypothesis says that there is a difference, and that difference can be on either side of the whatever value, whether it's 0 or there's no difference in means. One could be bigger, one could be less, it could be either. And the one-sided test just says that there is a directionality in the alternative hypothesis. So you think that one mean is greater than the other, or one mean is less than the other. So this is where type 1 and type 2 error comes in, because for any hypothesis that we test, there's always going to be a truth that we don't know. And we can either, we're going to reject or fail to reject the null hypothesis based on the results of our test, but that may be true or not based on what's actually happening in reality. So that's where we can break this down in sort of a 2x2 table. In the columns, we can see that this is what's actually true, what's happening in reality. So the first column says that the null hypothesis is true. So this is that in reality there is actually no difference between your two groups. And the second column says that the null hypothesis is false. So in reality there is a difference between the two groups. The two rows are the results of your testing at the end of your study. And as we said before, you can either not reject your null hypothesis and say that there is no difference, or reject your null hypothesis and say that there is a difference. So when there is no difference between the two groups, in other words, the null hypothesis is true, and you do not reject your null hypothesis, you're correct. So that's good. And alternatively, if there is a difference between the two groups and you do reject your null hypothesis, again, you're correct. So that's good. But what happens if you're false? So this type 1 error occurs when you reject your null hypothesis when in fact it is true. So what essentially is happening is that you're saying there is a difference between two populations or two samples when in fact there isn't. And that's type 1 error. This is denoted by alpha, and it's often referred to the significance level of a test, and this is usually set at 0.05. And this was just arbitrarily set a while back, and people have just kept using it. So that's type 1 error. Type 2 error occurs when the null hypothesis is not rejected, when in fact it should have been. In other words, so you said there was no difference between two populations, when in fact there is actually a difference. And this is denoted by beta. And common values for beta are 0.1 and 0.2. You don't usually set these unless you're doing sample size calculations, which is another thing. And the power of a test is actually 1 minus beta, and this is the probability of rejecting the null hypothesis when it is false. And that is this sort of quadrant right here. So that's saying the probability of finding a difference when there is a difference. That's the power of a test. So this is the same thing, but just shown sort of schematically. So the first curve is essentially your null hypothesis and the difference, the mean of whatever null hypothesis you're testing. And the second one is the alternative hypothesis. And you always test against the null hypothesis. So this value here is going to be the significance level that you've set already. And what this is showing is that if you change the significance level in one direction or the other, you're actually going to sacrifice either increasing type 1 error to decrease type 2 error, or increase type 2 error to decrease type 1 error. So they're interrelated. And all this gray here is the power of the test, everything to the right of this line. So we'll just look at hypothesis testing using this study that I found. So this is just an RCT looking at a knee sleeve versus a more functional ACL brace after ACL reconstruction. And the hypothesis of these tests was that there was no difference between a knee brace and a knee sleeve. And the alternative is that there is a difference between a knee brace and a knee sleeve. And this is the result. So essentially, I mean, they found there was no difference between any of these results. So the ACL quality of life is just a quality of life score. The KT 1000 arthrometer just measures anterior translation of the tibia. They have hop limb symmetry and an activity scale. So essentially at 12 months between brace and sleeve, they found no difference. So based on the results of these tests, in what sort of row would these guys be? So they found no difference.
So the top row.
Exactly.
So, yeah.
So based on the results of these tests, these guys could be right or they could be committing a type 2 error. And that sort of comes back to the p-value. So when you get at the end of it, and we can talk like a lot about p-values and how much weight to put on them or not. That's a whole other discussion. But essentially the p-value tells us the probability of observing the results of a test observing the results of the test or more extreme than what we observed on the assumption that there is no difference or the null hypothesis is true. So essentially if p is less than your significance level, which is usually set at 0.05, we would reject the null hypothesis. However, the p-value should be viewed more as like a continuum and just a strength of evidence. Having this cut off because a p-value of 0.045, you would say there is a difference, but a p-value of 0.051, you would say there's no difference. So, I mean, there's a lot of debate as to how much weight we should put on these and whether we should use Bayesian statistics for the difference, but that's just to bring up p-values briefly. Now we're going to go into comparison of means, so pretty quickly. So in order to compare means, you can compare one sample, two samples, or more than two samples. So comparing one sample, essentially this doesn't happen very, very often. I've done it once before, but essentially you're comparing a sample against a population. And where you'll see this done is if you have a sample and you're comparing it against like census data. Because that's the only way that you'll really have sort of population data. And to do that, that'd be a one sample t-test. And that's the t statistic that you calculate and then compare to a critical value that you would set based on your sample size and the significance level that you want to test. Two samples, again, so it'd either be a t-test or a z-test. A t-test essentially is what you would see more frequently because in order to have a t-test, coming back to what we said previously, you don't have the population variance or standard deviation, so you have to use the sample variance or standard deviation, and therefore use a t-distribution. Whereas if you did have the population variance, you can use a z-statistic, but again, that doesn't really happen that often. And essentially all you're doing is comparing two means to see if there's a significant difference between the two means, and what's going to influence that test is the difference between the two means right here. So you can see the standard deviation of the means and the sample size.
So if we were to use that, like for example, going back to that Western study on knee brace.
Yeah.
So you would be comparing, like for example, mean between, let's say if they did two knee scores.
Yeah. Yeah.
Oh, okay.
Yeah. I have another example coming up, but this
so
one.
No, it would be the mean of the knee sleeve versus like the more advanced knee sleeve.
Yeah, exactly. So all these scores are mean scores, right? So there's scores. So you do the mean of this versus the mean of this, and this is a t. I'm pretty sure they did a t-test or a Wilcoxon, which is a little bit.
Gotcha.
But yeah, so that's what they did. They compared the mean of this versus the mean of this, individually throughout. So if there's greater than two samples, when you want to compare the means of, say, 3 groups or 4 groups, like one of the questions is why can't you just do a series of t-tests? And the answer to that is what we talked about with type 1 error. So you're saying that on average, if you're using a significance level of 5%, 1 in 20 times you're going to incur a type 1 error. So if you keep adding on these t-tests, you're going to do more and more. You're going to increase the risk of incurring a type 1 error. So an Anova test or analysis of variance allows you to test multiple means against each other with a lower risk of type 1 error. So that's what this looks like. So people ask, why is it called analysis of variance if you're comparing means? Because essentially this is why. You can look, the variance in set 2 is much greater than variance in set 1, and just eyeballing it, you would say there's probably there's a stronger chance that these are going to be different compared to these. So essentially what you're doing, the big thing that changes between set 1 and set 2 is the amount of variance. And the one thing with Anova testing that you should know is that the hypothesis tests for Anova are similar, but there's a little bit of a nuance. So the null hypothesis is the same. So it says that all your values, all the means are going to be the same. The alternative hypothesis says that at least one of the means is different from the rest. So based on the Anova alone, you don't know which one that it is, or you don't know how many of those there are. So what you then have to do is go on to do other procedures to then try and tease out which mean is the significant difference. And there's two that are most popular, the Tukey or the Sheffe procedure, but that's not that important for this talk. So to look at who did this, and again, like I said, in order to find a study, it was hard to find a study that used the Anova test or t-test as their primary test to identify the inference that they wanted, just because most tests are really doing regression modeling right now, and you really should. Apart from like looking at differences in your table 1, but this study did. So we're not going to talk about sort of PRP and what it means and whether this is, this is not a great study. So this study did use an Anova test with a Tukey to look at differences in arthritis outcomes using PRP versus a placebo. So if we look at their results, so what they did was they did an Anova test to test differences in WOMAC, which is the Western Ontario and McMaster arthritis criteria. Let's see.
Yeah, that sounds about right. Yeah, Western Ontario Arthritis Index. No, go back, sorry.
Western Ontario and McMaster University's Osteoarthritis Index.
Yeah, I don't know how to get it's the Western Ontario, and then MAC is from the McMaster, even though it's technically Mick.
Yeah. Regardless. So what they did, they looked at these WOMAC scores. They gave half the individuals. So this is a sample size of 30. So 14 or 15 got PRP, 14 or 15 got placebo, and they looked at the change in the WOMAC scores over a few time points. So 1 week, 2 weeks, 2 months, 3 months, 6 months, and 12 months. So what they did is they looked at the change in the WOMAC score within a group from baseline. So they looked at baseline, so this is the PRP, this is placebo, and this is PRP, placebo for various domains within the WOMAC. So the Anova, they looked at, so they're doing more than 2 means, so they're looking at this change here versus this change here. Sorry, baseline to week 1, baseline to 2 weeks, baseline to 2 months, 3 months, 6 months, and 12 months, all within a group. And they used a t-test to look at placebo to PRP within each group. So that's just 2 means, right? Okay? So they found a lot of significant differences, right? So look at all the B's and C's, and we're not going to go through it. But essentially coming back to this, they found significant differences. So where would this lie in the hypothesis testing? Bottom row, right? So they're either right or they've committed a type 1 error. And that's going to come back to the next briefly thing that we're going to touch on. The last thing that we're going to touch on is, like we said, the reason why you don't do multiple t-tests and you do an Anova in favor of that is incurring type 1 error. So even within a study itself, you have to sort of take into account the amount of type 1 error that you can have within a study, and that has to do with multiplicity of testing within a study. So look how many things they tested, right? So they did a t-test, so 1, 2, 3, 4, 5, 6. 6 times 1, 2, 3, 4. So 24 t-tests plus 1, 2, 3, 4 ANOVAs on 1, 2, 3, 4, 5 means within each ANOVA. So that's a lot of testing. So we know that type 1 error, they're using a significance level of 0.05, right? So that's That means that one of these, at least one of these on by chance is a type 1 error, which means that they're seeing a difference that they shouldn't, that doesn't exist in reality. So that is what is called like multiplicity of testing, even within a study, and you have to be careful of and look for authors who are trying to adjust for that. And there's two ways that you can, and we're not going to go into the details of how it works, but it's just something to keep in mind when you're reading a study. If you see lots of statistical tests going on, whether someone has done an adjustment to the based on the number of tests that they're doing. There's two common ways that you can do it. It's called the false discovery rate or Bonferroni adjustment, and that just kind of tries to take into account all that type 1 error that you're incurring throughout a study. So that's the end of this one. I know it's very like bread and like kind of more basic stats, but we kind of needed this to build on these concepts to go into the next one, and the next one's gonna be a little bit more epidemiological based and a little bit more clinical, and we'll have more studies to go through. And if you guys next time want to have a study that you've read and you want to go through why they did something, I mean, I can try my best to go through it and see why. Any questions?
Can we go back to that last study? So this one here.
Yeah.
So this is where you're talking about they should have used regression analysis.
So they didn't have the sample size to do regression analysis.
Okay.
Based on the data itself, like these were appropriate